All right, let's just jump right in. We're going to be talking about networks today, but hey, not just any old network. We're diving deep into the super specialized, high-performance fabrics that are built for literally one of the most demanding things you can do on a computer, training huge AI models. And as you're about to see, the old rulebook for networking, yeah, you can pretty much toss that right out the window. And this quote right here, it just hits the nail on the head. Think about it. For a massive AI training job that's running across thousands of GPUs, being crazy fast doesn't mean a thing if that speed is all over the place. The whole system, every single part, has to move together, perfectly in sync. Inconsistency is the real enemy here. It's all about rock-solid predictability. So this brings us to a really critical idea called the all-reduce operation. The easiest way to think about it is like a mandatory team huddle for all the GPUs. They all have to stop, share what they've learned with each other, and only then can they move on to the next step. And here's the painful part. The entire multi-million-dollar job grinds to a dead stop, just waiting for the one single slowest GPU to report in. That's the bottleneck we're trying to solve.
Okay, so here's our game plan. We're going to start by really digging into what makes AI's networking problem so unique. Then we'll see exactly why traditional Ethernet just falls apart. And from there, we'll build our solution, piece by piece. We'll start with a lossless foundation, add the muscle with Spectrum X, give it a brain with UFM, and then finally, we'll see how it all connects to the cloud.
So, first things first, we have to understand the nature of AI traffic. And trust me, this is nothing like browsing the web or streaming a movie. It is a completely different beast with its own very demanding set of rules.
And wow, this chart just lays it all out, doesn't it? On one side, you have your typical data center traffic. It's kind of chaotic, right? Lots of little separate conversations that can handle a bit of a delay. But AI training? That's a synchronized symphony. You've got thousands of GPUs all shouting huge amounts of data at the exact same microsecond. A delay for just one of them isn't a small problem. It's like the lead violin suddenly stopping mid-performance. The whole orchestra just has to wait.
And that brings us right to the heart of the problem with using standard Ethernet for this stuff. You know, what's usually its biggest strength in a normal data center, its ability to handle random chaos, well, that becomes its absolute greatest weakness in the world of AI.
So the main culprit is a thing called ECMP. Its job is to balance traffic by basically just spraying packets randomly across all the available network paths. Now, for your normal internet traffic, that's awesome. But for AI's perfectly synchronized data bursts, it's a total disaster. You end up with a massive traffic jam on one path, while other perfectly good paths are sitting there completely empty. This randomness is what creates those unpredictable hotspots that just kill performance.
And the result is exactly what we're trying to avoid: inconsistency. That all-reduce operation, our team huddle, is stuck waiting again. But this time, it's not a slow GPU. No, it's a randomly congested network path. The whole job gets bottlenecked by just bad luck.
Okay, so that's the problem. How in the world do we fix it? Well, we have to start from scratch and build a network on a foundation that can guarantee that no data ever gets dropped. So let's see how that first layer is built.
The first tool in our toolbox is something called Priority Flow Control, or PFC. Now, old-school Ethernet would just slam on the brakes and pause an entire link. PFC is way more like a surgical tool. It can tell another switch, hey, just tap the brakes, but only for this super high-priority AI traffic. Let all the other stuff keep flowing. This is how we prevent packet loss for the traffic that matters most.
So here's how it actually works. Let's say a switch's buffer for that important AI traffic starts to get a little full. It immediately sends a very specific PFC pause message back to its neighbor. That neighbor then pauses only that traffic, which causes its own buffers to fill up a bit, and guess what? It sends a pause frame back to its neighbor. It's this chain reaction of back pressure that ripples all the way back to the original GPU, telling it to just ease off the gas for a split second to prevent any data from being lost. But, and this is a huge but, as critical as PFC is, it's also really dangerous. If you're not careful, you can get a situation where a bunch of switches are all telling each other to pause at the same time, creating a deadlock. And that's basically a network-wide traffic jam where absolutely nothing moves. So we have this amazing, powerful tool that can also blow up in our face. How do we manage that risk? Well, this is where the smart hardware comes into play. We need more than just clever protocols. We need a fabric that's built from the silicon up to deal with this stuff. And that's where NVIDIA's Spectrum X comes in.
And let's be super clear about this. Spectrum X is not just a faster switch you can buy. It's a complete end-to-end platform. It's the network card inside the server, it's the switch itself, and it's all the software that ties them together into one seamless, intelligent system that was born to do one thing: run AI.
And this table just lays out the difference perfectly. Look at the key shift here. It's moving away from random chance and towards real intelligence. Instead of that random ECMP routing we talked about, Spectrum X uses telemetry-aware routing. And here's the most important part. It's not just a standalone switch. It's a co-designed system where the NIC and the switch are constantly talking to each other.
You know, that co-design, that's really the secret sauce. The network card can literally tell the switch, hey, my buffer is starting to fill up over here. The switch hears that, looks at the bigger picture across the entire network, and then intelligently reroutes traffic to avoid the congestion before it even becomes a problem. The network stops guessing and starts knowing. That is what job-aware intent-based routing is all about.
So, we've got our lossless foundation. We've got the smart hardware muscle, but we are missing one last absolutely critical piece. The brain that controls everything. And that brain is the Unified Fabric Manager, or UFM.
You know, a traditional network management system, an NMS, is slow, it's reactive, it checks for data every few seconds, maybe even minutes, and then some poor human has to look at a dashboard and try to figure out what went wrong. UFM is the polar opposite. It gets real-time, microsecond-level data directly from the hardware itself, and it operates in what's called a closed loop, which just means the system automatically fixes itself in real time. It's not just aware of the network, it's aware of the actual AI job that's running. And this is just the perfect analogy. Using a traditional NMS is like seeing a warning light flash on your car's dashboard after something is already broken. UFM is like engaging the autopilot. It's constantly making thousands of tiny adjustments to see problems coming and steer around them, making sure your AI workload has a perfectly smooth ride.
And here, you can actually see what that autopilot's view looks like. UFM has this complete live map of the entire network fabric. It sees the health of every single link, the depth of every queue, and it uses that global, God-level view to make smart, predictive decisions, constantly guiding traffic down the best possible path. Okay, so we've built this absolutely incredible self-driving network for our AI cluster. But, you know, it can't just live in a bubble. How do we connect this beast to the rest of our company's infrastructure? And maybe more importantly, to the public cloud?
Well, the answer is to build a private, multi-lane superhighway directly from your AI fabric into the cloud using services like AWS Direct Connect. And this highway has its own special on-ramps and interchanges using tools like Direct Connect gateways and transit gateways to build a secure, super high bandwidth bridge. This really gives you the best of both worlds. You get that specialized on-prem performance for training, but with totally seamless access to all your data and services in the cloud.
So at the end of the day, if there's just one thing you take away from all this, let it be this. For AI, consistency is king. It's more important than raw speed. We have to stop thinking about the network as just a collection of dumb, fast pipes. It has to become a single, intelligent system that can actually understand and adapt to the crazy demands of these AI workloads.
And that really leaves us with a pretty fascinating question to think about, doesn't it? In this new era of AI, have we finally reached a point where the intelligence of the network, its brain, is actually more important than the raw speed of its connections, its brawn? It's definitely something to chew on.